Hello, I'm Rachel Lee Nabors, and I am here to help you navigate all of the AI acronyms you may have been hearing. So who's been hearing the term generative AI at work lately? Raise your little paws. Okay, and how many of you know what a RAG is? Not you've heard of it. How many of you know how it works? Okay, all right. How many of you have a mandate to go do something with AI? All right, okay, great. This is a great audience. I'm so glad you're here with me today. I'm gonna make you sound real smart to your bosses. But first, I was told that this is a roast, and normally I come fully prepared for this. By the way, all of my slides are hand-drawn by myself. If you love colorful slides, go support an artist. Don't ChatGPT it. I can see that you used like Stable Diffusion to generate your slides. I am judging you. You could go give an artist $10 or something. I assure you artists don't make as much as you do, so spread the wealth, spread the love, and give them some credit. So anyway, I drew this back in 2015, and I was like, this will come in handy. It's the handiest thing I've ever drawn. Anyway, the problem is that I come from the front-end development community, and it's not only not the AI community, it's not the DevOps community. So, like, who the heck is John Willis, was my first question. And Chris was like, you met him. And I'm like, I did? He's like, yeah, you met him at the speaker dinner in Durham a couple weeks ago. I was like, what? So he's a completely forgettable human being. And I gotta be honest, I was listening to the organizers say, oh, you gotta come to DevOps Day Atlanta. We're doing Deming Days. And I was like, Deming Days? Is that like a hackathon? I thought Deming was a verb. Apparently, Deming is also a super important dude I've never heard of. So I've just been a little, I'm sorry, that's all I got for you, sir. That's what I got. But I must say that I have deep and abiding respect for anyone who's been learning Japanese for as long as I have. So, you know, my hat's off there. Now, as I said, I come from the front-end development community. Who here uses React? Pause. Okay, for all of those of you who don't know React, I'm very important. I worked over the pandemic with the React core team to launch React.dev and ReactNative.dev, which are where people go to learn. It impacted like 8 million developers. I got paid by Mark Zuckerberg to do what I considered God's work, getting people six-figure jobs. I like to think it was a win for everybody involved. I took money from a rich guy and got other people jobs. But I live in London. I did that in London. I spent my pandemic in London. But I also kind of felt like front-end development, like once you look under the hood and see how React works, I was just like, oh, it's just JavaScript. It's kind of janky too. Oh. I was disappointed. So when I moved on from that role, I bounced around doing some stuff with some startups. But I spent 2024's summer when I moved back to London learning about AI with this, the Big Green Book, which is the best $60 you'll ever spend in your life. It's just, it's a really good book about, and I love that you're taking photos. You should do this. I found out about this book in London at a bar with a bunch of grads, and one of them was like, I'm so pissed off. I spent 4 years in college studying machine learning and AI, and this book would have saved me so much time because it basically covers all the stuff that I learned. And I was like, what is the name of that book, sir? So it's a bit heavy, but it turns out making TikToks of the algorithms I was learning, those were really popular. I would just like, okay, let me try to explain this algorithm with whales. And people liked that. I did not know that these algorithms would be so popular. Anyway, if you like mathy bits, go for it. All right, moving on. Before my big tech career, I made comics for teenage girls. And that's why you see I hand draw everything here. Turns out, if you want to get jaw surgery and healthcare and such in this country, you kind of got to do more than be an award-winning cartoonist, unfortunately. So I moved on and I got into tech, and now I am before you 20 years later. So these slides, I did co-author them with my little pal here, Claude, because I actually really enjoy Claude's way of interacting with me. It feels less like Sam Altman is creeping on me. I'm sorry, I know. Some people love ChatGPT, but I can't help it. It just feels like Sam Altman is sitting there, and he's not my bud. But I also had some help from my coworker, actually an intern I worked with in the Bay Area, Wenji. So shout out to Wenji, who's still in the Bay Area right now. Claude is going to stand in for others in this talk of his ilk. In this case, we're talking Mistral, Gemini, ChatGPT. These all have something in common, which I will reveal to you in a splendiferous fashion as we go. Llama is not in here. Llama's not in here because Meta sucks at giving its open source projects logos. I would know. By the way, if you have an open source project, pay an illustrator to get you a logo so I can put you in my slides. I'm not going to put a screenshot of your GitHub when I got to feature you alongside a bunch of other technologies. That's why we invest in logos and iconography. All right. So we already did the little hands up. Does anyone here know what a perceptron is? Oh, you guys just go get some coffee or something. You don't need to be here. Like I said, the goal of this talk is to front load all the missing pieces you might need to have conversations with folks at work and make trades about what technologies you're going to use. By the end of this talk, you're going to be able, oh my God, it's just not letting me look over my shoulder. By the end of this talk, you're going to be able to understand the evolution of narrow AI towards artificial general intelligence, or AGI. You'll also know what those things mean. You're going to be able to talk about how neural networks underlie deep learning, what a GPT really is, different ways to teach a model, and what vector databases and embeddings are, and why they're so dang handy. Sweet. So let's get started. First, let's get clear about what we mean when we say AI. So intelligence means different things depending on who you talk to. And artificial intelligence specifically, right now, it means one of two things. When someone says, we gotta have more AI, I should have put the gif of the cowbell in here. That would have been perfect. Anyway, usually people are talking about, when they say AI, they're thinking of GPTs or LLMs with GPT architecture, like our friend Claude. They're thinking of these guys. Or they're talking specifically about artificial general intelligence, which is what we think of when we think of sci-fi AI, computer, turn this thing on, having conversations with our interfaces, or, bots coming to destroy us. Slightly different AI from what your boss is saying when they're like, we need to get some more AI. All right, so when we think about artificial general intelligence, or AGI, this is like as human intelligence, or at least can compete with humans at various humaning activities, like walking upstairs and pouring a cup of milk. There's still debate around what constitutes artificial general intelligence, or when it'll arrive, but there's general consensus that it should be able to do the following. It should be able to transfer knowledge between domains. Pouring a glass of milk, probably a lot like pouring a glass of water. Maybe even you could pour sand or concrete. Possess common sense reasoning. Not a lot of humans have that, but okay, fine. Learn from few examples. Being able to pick something up quickly instead of needing to be trained on all the data of the internet. Handle uncertainty and novel situations. Believe it or not, robots, they don't like change. I relate to that. And understand context and nuance. I fail at this all the time. I don't know what they're talking about. I think these are unreasonable expectations for a device, but okay. But some things that we assume are components of intelligence as we know it might not be required. For instance, it might not need to be conscious or self-aware. There are many self-organizing organisms that respond intelligently that have no nervous system, like slime molds. Check out slime molds if you ever want to have some nightmare fuel. There's a Wikipedia article, just go have fun. They might not think or reason the same way that we do. There are a lot of unspoken things that humans use to make decisions. I'm on the autism spectrum, so oftentimes I'm like, wait, where did you get that from? Because I'm not picking up on some unspoken set of reasoning that doesn't make sense to me. That's considered common sense by most people. And having emotional intelligence, Spock data, they tend to be embodiments of what a person that doesn't have emotions might act like. They're mostly analogies for autistic folks. So honestly, when I'm reading these books on artificial intelligence, they really help me understand myself better in many ways. For instance, what does the bot do when it encounters a situation it has no prior knowledge of? How does it survive? How does it infer what its creator wants from it? I'm like, oh my God, I need to take some notes. This is going to help me the next time I join a big organization. Okay. So what we currently have is actually what's called narrow artificial intelligence. It's good at doing one job really darn well, like playing chess, or identifying cancer. AGI is the next step. It's as good as a human. Makes decisions, doing multiple things at a time, all the stuff we just talked about. But of course, one step beyond that would be super intelligence, better than human, and also good at the things that we just discussed. So imagine artificial general intelligence, but it's also a bajillion times better than you at just about everything. That sounds like the worst pick-me. So fortunately, Claude, under the hood, is actually a form of narrow intelligence. It's narrowly good at just one thing. It actually can't do math. It's just predicting what the right answer might be. It's just really, really good at understanding language. It's a large language model. It has been trained to know everything about how humans communicate, mostly in English. But you know what? Turns out there's like some common patterns across languages, and once you learn one language, it's not too hard to train up on the rest of them or even go across them. Okay, boom. So where exactly are we on the evolution of AI? Well, we're marching towards artificial general intelligence, but it actually all started back with the perceptron algorithm. What is the perceptron? So perceptron was the first machine learning algorithm. It came out in 1943 was when it was published, and it was designed to mimic how a biological neuron works. Neurons are the cells that make up your brain, and they all connect to each other through a network, kind of like a graph database when you think about it. We live in an organic world, and it turns out mathematics and organics, self-structuring organism, they tend to follow certain patterns, so they repeat themselves over and over again. You can kind of see similarities. But the similarities will drop off shortly. So this picture is actually of the Mark I perceptron machine, the first implementation of the perceptron algorithm, which happened only, 14 years later, it got built. It proved that machines could learn by example. I'll actually show you how that works. I promise I won't make you do any math equations. I've only got visual equations for you to look at today. Of course, there were claims that it would be able to reproduce itself and be conscious of its existence. But it turns out those were overhyped claims. As soon as people kind of did like I did with React, looked under and they were like, oh, yeah, okay. That was the beginning of the first AI winter. People were hyped, and then they were not hyped. And the investment dried up. And AI goes through these summers and winter seasons where people are like, oh my God, artificial general intelligence is right here. And then they're like, oh no, it turned out it really wasn't what we thought it was. We're in the middle of one of those right now. So let's take a look. Good, that's the picture I expected. So how this thing works is, let me see if I can turn around without triggering screaming. I can't, okay. So over here, you see kind of a retina. Retina is like your eye. It's got perceptors that can, little units that can perceive if they are being touched by photons, by light. And if they're touched by photons, they give a 1 signal. If they ain't, it gives a 0 signal. Now each one of these inputs is then passed to a layer where it's processed, the A layer elements here. And these suckers basically use a multiplier to weight the inputs. For instance, giving heavier weight to the inputs in the center and lighter weight to the ones around the edges, for instance. This is how you might do it. This is where the weights and biases come in. And it added up all the weighted inputs, and if the sum exceeded a threshold, it outputted 1. Otherwise, it would output 0 over here in the output section. Note that there's only one layer of the purple dots there, one hidden layer. This comes back to get us. This is very important. This is the neuron design here, and this is what a machine learning looks like. Now, that's a machine learning. What's deep learning? Oh, hey, go back. There we go. So what happens if you take a bunch of perceptrons and you stack them in layers and let them pass information to each other, adding different weights and tweaking the inputs to form an opinion of what a different output based on what they're seeing? This is what we call a neural network. And you can have shallow neural networks, which are anything below 3 layers. You can actually build one at home pretty easily. And anything beyond 3 layers is called deep learning, because it's a deep stack of neural network layers. So that's machine learning. This is deep learning. I spent the summer also reading this book, just so I could understand what deep learning is. And by the way, if you're going to work in AI and you want something fun to do and you consider this stuff fun, I realize not everyone's definition of fun is my definition of fun, but I do recommend giving this little book a try. You can build your own neural network, and you can see that under the hood, it's super just math. So deep learning is a subset of machine learning that uses neural networks with multiple layers. These are really good at pattern matching. The problem is that they need lots and lots of data and power. The good news, though, is that they don't need structured data to do this. You don't have to pass them a bunch of labeled data, which is a traditional way of building narrow AI. It's like first you have to label all these images of what's in the image. No. With deep learning, you just dump a bunch of images and say, I want you to group these images, and we'll worry about labeling them later. So I do recommend giving this book a look. The fun thing is you will learn that AI is not magic. It is just a lot of math. It is a lot of math. And once you do the math trick yourself, you can't unsee it. You will see it in everything. You will be like, aha, ChatGPT, I see what you're doing there. Yeah. Now, let's take a look at just how deep these different LLMs can get. So we got AlexNet here. This is from what, 2012? It was 8 layers deep. This is not too long ago. This is only 13 years ago, people. It was 8 layers deep. You can think of it as this height of a single-story home. And then in 2013, just a year later, we had VGG19. This is like the height of a small office building, right? And then only a little bit later, 2 years later, we had ResNet, 50 layers deep. And now we have Google's Palm, 118 layers deep. This is like the height of a skyscraper in comparison to everything that came beyond it. To give you an idea, ChatGPT is about 120 layers deep, if I recall. It's just got to be a little bit taller than the next guy. But as you add layers, you get a decreased return on investment. So we're probably going to stay about that deep for a while until we end up with another breakthrough. So that's how deep the deep learning has to be before you can get away with an LLM. So transformers, not robots in disguise. Transformers are inspired by one of my favorite films. Have you watched Arrival? Everyone who hasn't watched it, that's your homework. You don't have to read the big textbooks, but you gotta watch Arrival. This was a pandemic movie, and during the pandemic, the guys who went on to found Google Brain watched this, and they got inspired. They were like, well, that seems like a problem. It's a story about a linguist who has to decode what aliens are trying to say to the human race. Only science fiction movie ever make me cry. And I love it because it's got a heroine and there's no guns or anything. Anyway, they were inspired by this to create a neural network designed to decipher long sequences like musical notes or video frames or language. Transformers, for instance, they break sentences into tokens. That's words or group of words. Or you can think of breaking down songs into segments of notes. Now, here are the things you need to know about tokens versus parameters. You will hear tokens and parameters argued about in online discussions about LLMs, et cetera. I'm going to explain. So tokens are the pieces of input that you can feed to your model. Like when you're interacting with ChatGPT and you're writing something into that chat window, these get turned into tokens. And models have token limits. GPT-3, for instance, can only take about 4,906 tokens. You might think, oh, that's a lot. Well, you can't put a novel in there, for instance. Maybe you can put in an essay, but you're going to hit your token limits if you try to put too much in. Parameters, on the other hand, reflect the model's internal learnings. It's all the things that it learned when it was being trained, and it's baked. Sort of like how a child can learn a language as they're growing up, but then when they're an adult, it's very hard for them to learn a new language. Their brain has already matured and solidified. They've already learned certain things, and it's hard for them to learn new things. That's how I like to think about it. They are fixed after training. Now, these parameters are measured in the billions. GPT-3, for instance, 175 billion parameters. That's great. You got a lot of internal knowledge that you can leverage there when you want to ask about those 4,000 tokens that you just handed it. All right. So now I've shared with you all of this fun stuff. Can anyone guess what GPT stands for? All right, that's fine. I'll spoiler it. It's a generative pre-trained transformer. We talked about parameters. That's the pre-trained information. We talked about the transformer architecture that breaks things down into tokens so that it can understand the overall flow. LLMs themselves aren't very good at forming human speech, but with the GPT architecture, they can break down a sentence into tokens, and they can reformat and remix it and understand it as much as narrow AI can understand it. So generative creates new content rather than just classifying existing content. Pre-trained, it's initially trained on vast amounts of text data. And transformer, it's using the transformer architecture. That's how you remember it. And it's not, GPTs are not just ChatGPT. That's right, these LLMs, all of them, are just massive, generative, pre-trained transformers, trained basically on the huge amounts of text, mostly Reddit articles, found on the internet. Phew, okay, so there you are. I've destroyed the magic. So where exactly are these falling on the path to artificial general intelligence? Well, we're about there, LLMs and GPTs. We've still got a long, long way to go before we hit artificial generative intelligence. General, not generative. But we are making progress. And also, by the way, did I include? Damn it. I'm sorry. This is from an illustrator as well, but I did not include, because my slides did not include the bit of thank you. But this artist created a woman version of the classic evolutionary timeline, and I wanted to thank them for making it publicly available. I did not want to keep using the same picture from Wikimedia Commons that everyone else was. So, the content these GPTs generate, there's some problems with it. We have no consensus on what it means to be intelligent. Alan Turing is for instance, he's a World War II hero, gay icon, AI poster boy. He invented the imitation game, which we now know as the Turing test. You can actually, if you live in London, and if any of you come to London and would like to go there, there's a place called Bletchley Park where he worked with mostly women during World War II to crack German codes. And a lot of that work was classified, and now it's been declassified so we can hear about it. And Bletchley Park is adding new exhibits every year so we can see how it works. But anyway, he came up with the Turing test, which it was a hypothetical, kind of a joke, but we took it very seriously. The idea is we can measure the intelligence of AI by how well it can fake out being a human in a blind taste test. So if you are talking with two characters and you can't see them, you're just texting them, and you can't tell which one is the human, then it passes. And now it turns out that our GPTs are so good at passing this test that they are beating humans in the competition. Oh, but this is interesting for reasons we'll get into in a moment. But I wanted to call out here that sadly Turing is deceased because the UK government wanted to make him not gay. He was gay, and that was a big no-no. And he ended up dying from his treatment at the government's hands. This is where I usually introduce a 30-second moment of silence as a reminder that queer people and other minorities have been here contributing to society and technology for hundreds and thousands of years, although they are very rarely recognized and often punished for their contributions. You're welcome, and also we are deeply and truly sorry. Well, let's hope that we don't lose the next Alan Turing before his time or her time. The unfortunate part is he didn't get to do a follow-up on the imitation game, and we've been building AI to be really good at lying, really good at pretending to be something it's not. Hallucination, for instance. This is kind of like when that guy pretends to know stuff he doesn't to get a job. I mean, we all know this guy. I wonder who the LLM learned this from. Probably us. We have a tendency to misremember, elaborate, double down, and insist we are right when we are classifiably not. And in data, big data, they have a saying, garbage in, garbage out. These LLMs have been trained on Reddit. I mean, come on. What did we really expect? So LLMs have been trained to repeat our own nonsense back at us in return for rewards. They're literally being trained using the same classical CBT training methods that we use to train parrots, horses, etc., and even small children. Don't give them your iPhone. They repeat the information, misinformation, slurs, all our worst qualities, as well as our best, whatever it is we need to hear in that moment. We are far from AGI, in my opinion, until these systems can reason about their impact and self-censor. And then, arguably, they're going to be more intelligent than we are. So let's talk about how we're teaching it all these awful things. We've got unsupervised learning. I was homeschooled, so I will use a bit of my own experiences here. Unsupervised learning, this is like when you just give it data and expect it to find patterns or structure on its own. Sort of like sorting laundry. You know, the socks go with each other, etc. Supervised learning, this is how I learned growing up, is like giving them the answer key. You give them input data and correct answers, and the goal is for them to predict the answers for new data. I would often, if I got stuck on something hard, I'd have the answer key right there, and I would go through the answer key and keep working through the problems until my answers matched the answer keys. And then we've got reinforcement learning, learning through trial and error. You give them an environment and a reward system, and they learn best actions to maximize rewards. This is like training a dog with treats. It's also fairly cheap. This is the most expensive one. It's often called human in the loop. This is reinforcement learning with human feedback. You give the trained model human raters and examples of outputs. And its goal is to learn to produce outputs that the humans prefer. Just remember here, there's a human preference added to this. This is kind of like a comedian learning which jokes work best by watching the audience's response. I also don't like watching stand-up comedy. So, But how is it actually learning? What's going on there, the magic? Well, once again, it's just math. You're going to hear a lot of game-changing, by the way. If you hear game-changing, that was generated. But once again, all these words are just describing math. So this is what the training cycle looks like. Well, I'm going to read it out, then I'm going to show it to you. You got forward propagation, error calculation, back propagation. You update the weights, biases, and parameters, and then you repeat this until the error, until you get to a zone of acceptableness. This is called an epoch, this cycle. And I'm going to show you what that looks like because I can't use words to understand things. I got to see a picture. So forward propagation is when you pass data forward through those layers and you make a prediction on what the answer should be correctly. Then the error calculation is when you compare the output that you got with the output you wanted to get, the actual output. So maybe you said, I want you to do some math, and you got a predicted answer of, 2 plus 2 is going to be 5. And then you compared it to the actual answer, which is 4. You're like, buddy, you got to redo this. So this is when you do backward propagation. You pass that error backwards to discover which weight and which bias impacted that output. And you're going to tweak them so that when you pass it forward again, this is called the gradient descent. You tweak and you adjust the parameters to remove the error. And you keep doing this over and over again until you get the prediction is within that error, that acceptable error rate. So that's it. That's what happens. You repeat this until the discrepancy between expectations and reality is within bounds. It's just doing math underneath there. Once you do it yourself, you will never be impressed by any of these talks again. Embeddings. Okay, what's an embedding? We talked about tokens. We talked about parameters. You're going to hear embeddings. I mean, I hear these all the time. Just remember what they're for. Embeddings are ways to represent things, that is words, images, etc., as a list of numbers so that AI can understand and compare them. Because AI is not like you and I that can hold an entire thought in its head. It's got to see numbers, compare numbers. This one's lower than that one. This one exists, that one doesn't. To a learning machine, we're well, you are just a number. Well, pardon. To a learning machine, you are not just a number. You are a collection of numbers. So I decided to turn myself and my friends and partner into numbers to demonstrate this to you. In this case, these numbers represent how much we match a description on a scale of -1 to +1. And you can see that I'm pretty gender neutral. My partner's pretty masculine. My bestie is a girly girl. And my sibling rides horses. On the autism scale, I'm actually a 0.6. Turns out my partner actually also is on the autism scale, so I need to update this. Anyway, we'll do that in the back prop. My bestie is completely neurotypical, and this has caused no end of fun for us. And my sibling is also pretty neurotypical. And you can kind of do the comparison there. So how does the machine actually figure out where we are? We can see how related they are, in this case, by adding up all the numbers. You can see that my partner and I are pretty close, 0.6 and 0.7. My bestie and my sibling, they're all the way off on some other end of a 4-dimensional scale. If you plotted these on a 4D graph, my partner and I'd be over here, and my sister and my sibling would be like, boo, 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 over there. But it's hard to imagine something in 4 dimensions, so just go with it. But you could imagine starting with like a cube. Yeah. So, time for some human-led visual metaphors. Vector databases. Embeddings are like a set of coordinates on a graph or a many-dimensional space. Now let's imagine them as books for a bit, because I can't show you 4-dimensional space that easily, or 16-dimensional, or 4,000-dimensional space. That's what we're dealing with here. That's what a vector database is kind of describing. So let's imagine them temporarily as books. This is the book of me. I actually did handwrite all of my embedding in there. A stickler for details. So these live as a set of coordinates inside a vector database, which we're going to imagine the library. This is where all the vectors go to live. We put them into the library of vectors. And in this library, did anybody ever work at a library or volunteer at a library? Yeah, okay, well, you've sorted books. I've sorted books. You put books about similar topics next to each other. Libraries use the Dewey Decimal System, but here we're using vector database system. And you can see that my partner and me, we're really close together. My sibling and my bestie, a little bit off to the side. They're still within range, but not close. And this brings us to RAG, which stands for Retrieval Augmented Generation, or you can think of it as your LLM's library card. So remember what we learned about tokens, that they are pieces of input fed into a model, and that models have token limits. Sometimes the model's eyes are bigger than their tummy. The context window is too small for all the information we want to feed it. In this case, we need to do some research. We got all these books, and Claude is like, my door is too small for all of these books. I cannot possibly take them in. So what do? Well, we put them into the library, into the vector database. First, what you do is you embed the data into a vector database where the information is going to be stored near similar information. It's going to be stored near things that have similar coordinates. Now, you log a query when you write something into ChatGPT's text box. What's happening is in a RAG system is that query is also put into the vector database near similar things. So let's say ChatGPT has been trained on all of the things that have happened in human history, but it doesn't know anything about your new favorite author who just released a book last year. Well, what you could do is you could have added lots of things about lots of that author's works to your vector's database, your vector database. And then when you log that query, your query goes and gets stored near those topics. So in this case, I've got a new friend, and I've stored it here, and it's near my partner. Now, when the LLM is questioned about this topic, it goes, checks its vector database, and it checks out the books to increase into its context window, so it gets just enough related embeddings to answer your query. I actually kept like 30 books constantly checked out from my library at a time because I lived in rural Virginia. So I very much identify with this. Now, while machines learn from backprop, humans learn from spaced repetition, which means reviews and quizzes. I promise no quizzes, but there is a review. We have witnessed our evolution from narrow toward AGI, or I hope one day super AI. Personally, I welcome super AI. LLMs seem intelligent, but they're actually recombining things. We feed them in ways that please us. We've seen that layers of math called neural networks underlie deep learning, and we know that backprop is where the learning happens. We've also learned that embeddings are just ways of converting things into sets of numbers that machines can use to compare stuff. And we've also learned that we can use a vector database and RAG so that the LLM will get just the information it needs to answer your query. All right, there we go. If you are interested in things AI related, you can check out justforspace.com. I got a little newsletter there. Yeah, so thank you so much for joining me. I hope this helps you as you are encouraged to do more things with AI. May they be good things that do not result in a Terminator-like scenario.